Okay, in this one we're going to go through and do the second fundamental theorem of calculus, second FTC. But most of the notes, and you'll see most of the homework too, is actually just going to be a mix of some review questions. So here in the notes, we're going to do 5 derivatives, and then we'll do 5 integrals. And then this is just going to kind of be like a review of some stuff we've done, some product rule, quotient rule, chain rule, some regular integration, some U-sub integrations. These 10 questions, 5 derivatives, then 5 integrals, just kind of a mix of some things for us to go through and to practice. If you want to, if you're watching this video at home and you, for some reason, missed class, you should probably pause the video and then try to do these 5 derivatives really quickly on your own. And then whenever you're done, unpause it and watch me go through them. Or if you want to just go through them together, that's okay. But you really should be able to do all these and really should be able to do them all fairly quickly. Yeah, if you want to, pause it, do the videos, do the questions on your own, and then just resume playing when you're ready. All right, so let's go ahead and just jump into this first one. It's just power rule for everything. So we have y equals 3x to the 4th plus 2 over x minus 12x to the 3/4 minus e squared. Be careful. Remember, e is a number just like pi. So the derivative of e squared is not going to be 2e. The derivative of that's just going to be 0. But here we go, just using the power rule. The exponent multiplies to the front and then decreases by 1. So this would be 12x cubed. That's x to the negative first power. So that negative 1 would multiply to the front, and then it would decrease by 1. So you'd have negative 2x to the negative second. So I'm going to write that as minus 2 over x squared. This 3/4 is going to multiply to the front. Negative 12 times 3/4 would be negative 9. And then that exponent is going to decrease by 1. So you'd have a negative 9 over x to the 1/4, which is a 4th root of x on the bottom. And then, of course, the derivative of e squared is just 0. It's not minus 2e. This is it. If you wanted to leave it as with the negative exponents, that would be fine. Minus 2x to the negative second minus 9x to the negative 1/4. That would be perfectly okay. I don't really care which one you do. The instructions say don't leave the negative exponents. Yeah, okay, I don't really care. If it says something like this on the AP exam, then for sure get it like this. But honestly, for the notes and for the homework, I don't really care. All right, next one is going to be product rule. I have this first chunk, and then I have the second chunk. There's also going to be a chain rule within that second chunk. So here we go. To take this derivative, which involves multiplication, I need product rule, which is the derivative of the first times the second plus the derivative of the second times the first. F prime g, g prime f, but don't remember it with f's and g's. Remember it as the derivative of the first. So that'd be 15x to the 4th times the second. So I'm just going to copy that sucker. Plus, then I'm going to need the derivative of the second times the first. I'm going to just copy the first because you don't have to do anything. And then the derivative of the second would be 2 cosine 2x. Right? The derivative of sine is cosine, and that extra 2 kicks out because of the chain rule. Here we go. We could rewrite it. 15x to the 4th sine of 2x plus 6x to the 5th cosine 2x. All right, cool beans. Next one is a quotient rule. I have the top and I have the bottom. Could I rewrite it and do product rule? Yes, but you also just sometimes need to be able to do quotient rule, so let's just do it. I need the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So here we go, g prime. The derivative of secant, the derivative of top. The derivative of secant is secant tan. So the derivative of the top times the bottom minus the derivative of the bottom times the top. All of that's over the bottom squared. X cubed squared, that's x to the 6th power on the bottom. So let's see, we have x cubed secant tan. Am I still on the screen? Oh yeah, just barely. Minus 3x squared secant over x to the 6th. If you were to leave it like that, That's fine. You will have some x's that reduce. This one's got 3 of them, that one's got 2 of them, that one's got 6 of them. So it looks like 2 could reduce from everything. So then you could rewrite it. You could also factor out a secant. Let's see, if I cancel 2 x's, let's see, that would be 4. Those would be gone. One of them's still going to be left. And then you could factor out a secant if you really wanted to. So we could have secant, and then in parentheses, x tan x minus 3 over x to the 4th. That's kind of the simplest version of the answer, with it all simplified and then factored as far as possible. There was really nothing wrong with how we had it written before, but if it wants you to simplify, you just may have to do a little bit. Okay, 4th one is going to be a chain rule question. Just a 2-layer composite. I have something to the 4th power. Then I have that inside something 2x to the 5th plus 3. Need to account for both of the layers of that composite, taking their derivatives by using chain rule. Here we go. The derivative of the outside piece, something to the 4th power, would be 4 something cubed. Whatever was inside getting raised to the 4th. That same thing copies, and now it's getting raised to the 3rd. So that layer is accounted for, and then you have to do chain rule. You have to account for what that inside function was. So times, then I need the derivative of this inside piece, 10x to the 4th. And there you have it. That's fine. I'm going to simplify it a little bit. I have 40x to the 4th. Then I have the chunk in the parentheses, 2x to the 5th plus 3, all cubed. Okay, so that is probably how the answer would look on a multiple choice question. Take it for what it's worth. There's nothing really wrong with that. You just have to simplify it. Okay, next one is a 3-layer composite. And if you need to, you could rewrite this as sine 5x to the 4th. All of that getting cubed, right? Sine cubed is the same thing as sine cubed. Doesn't matter whether you write it like this or like this. I think this is actually a little bit more helpful because you can see the 3-layer nature of this composite. You have something getting raised to the 3rd power. That's your outermost framework, something to the 3rd power. Then you're going to have a sine of something. That's your middle layer. And then your innermost piece is the 5x to the 4th. So I'm going to have to take the 3 derivatives, which means chain rule is going to link them all together, right? I'm going to multiply by the derivative of both of the inside pieces. Here we go, h prime. The derivative of something to the 3rd power would be 3 something squared, whatever was inside, getting cubed. Now it's inside, getting squared. So this will be sine of 5x to the 4th. That layer is accounted for. Now account for the middle layer, sine. The derivative of sine is, cosine. Whatever was inside of the sine, which was this, goes inside of this. So the derivative of sine is cosine, and then I have to account for that thing that was inside the cosine or inside the sine. The derivative of this layer would be 20x cubed, and then you would probably just want to simplify it. Look at all the constants. You have a 3 and a 20, so that's a 60. You have an x to the 3rd power. Then you have a sine squared of stuff, cosine of stuff. There we have it. That's probably what the answer would look like on a multiple choice question. Okay, so there we go. 5 derivatives, some practice with all of the derivative rules, product, quotient, chain, of course, just the regular power rule. Hopefully those are okay. The next couple of examples are going to be integrations. I'm going to scroll it up. So again, if you need to, if you want to practice these on your own, pause the video and then work them and then unpause it when you're done. There's going to be 2 more on the next page. So you can copy these, right? Freeze the video, pause it if you want to work them out before we go through them. And then we'll also have these 2. Okay, so you can go ahead and pause it and do these 2 also, but we're going to go ahead and go through them. Okay, so pause the video on one of those previous pictures or one of those previous still frames if you want, and we're going to integrate. Remember, integrating is when you add 1 to the exponent, then you divide by the new number. Okay, I'm tilting that the wrong way. Let me try to orient it a little bit more horizontal. Okay, here we go. All right, integration. Add 1 to this exponent, divide by the new number, so that first term is going to integrate x to the 3rd power. If you can just use pattern recognition, right? If you just know that this is the derivative of x cubed, just work your way backwards. Okay, now here I have 5x to the negative 4th. If I wanted to add 1 to the exponent, Negative 4 plus 1 would be negative 3. Then I would take this coefficient, which was a positive 5, and I would divide it by that negative 3. So look, it's going to end up being a minus 5/3 x to the negative 3. So minus 5 over 3x cubed. That's how you could write that antiderivative. That's how you could write the integration. And then the integration of a 2 sine. I know it's going to have be a 2 and a cosine, but if this was a 2 cosine, the derivative would have been negative 2 sine. Since that's positive on the derivative, I know this must have been negative. So x to the third power minus 5 over 3x cubed. You could rewrite that as minus 5/3 x to the negative third. Like those are interchangeable, don't matter. Then minus 2 cosine x, and then of course for indefinite integrals, of course, you put the plus c. So there we have it. Next one is a definite integral. And you could avoid u sub if you wanted to. If I just multiplied all this out and then took this extra x squared and then distribute it, right? You could expand it into a polynomial. Once you've done it, then you could integrate, then you could plug it in. But we can also integrate while it's more factored. You just have to use u substitution. Okay, the x values are 1 and 2, so I'm going to put the squiggles for the u values. I could find them, but I'm not going to bother. U would be equal to this chunk, x cubed plus 1. Remember, there must be a relationship between these two chunks. One of them has to be the derivative of the other. And the one that's the higher power term, or the one whose derivative is also there, that's the one you set as u. You don't set the derivative piece as u. You set the antiderivative piece, which is usually the bigger term, but it's also going to be the term that has something happening to it. So that's my u. Take the derivative, 3x squared, kick the dx over, 3x squared dx. That's what du would be equivalent to. I have the x squared like I'm supposed to, very good. I have the dx like I'm supposed to, very good. I'm missing the 3, oh well. Right, that just means the u substitution will kick out a 1/3. Now I'm going to translate it all over. It starts with x, going to translate it all over. We have that 1/3 integration from squiggle to squiggle, and then I have u to the second power du. I've translated it all over to this u integration. But very wonderful. Now we can integrate it. Don't forget about that 1/3 out in front. Then I integrate it, so it'd be 1, that's ugly, 1/3 u to the third power. And then we can reverse substitute. So this is going to be a 1/9 x cubed plus 1 to the third power. Once I've reverse substituted and I'm back to x's, then I can go back to having the x limits. Now we can go through and plug it in. And then we would have, you can either attach the 1/9 or leave it factored out. I'm just going to attach it. I have a 1/9, let's see, 2 to the third power plus 1. So that's 8 plus 1, so that's 9. So I'm going to have 9 to the third power. Oops, wait, nope, yep, okay, yep, that's right. That's my upper evaluation, and minus the lower evaluation would be 1/9. If I plug in 1, 1 cubed would be 1, 1 plus 1 is 2, so I'd still need to do 2 to the third power. So here's my upper evaluation coming from plugging in 2. Here's the lower evaluation. How wonderful. So you could have, like, instead of leaving this 1/2 kind of attached to each term, you could have just taken this sucker out and then had the 1/9 out in here, and then that 1/9, right, everything would be affected by it. And then you could distribute, or you could leave it in there. It honestly doesn't matter. Sometimes I do it one way. Sometimes I do it a different way. It doesn't matter, right? It's your own personal preference. Okay, here we go. So let's see. We got 9 to the third power. That is 729. So we've got 729 over 9 minus 2 to the third power is 8. So that's 8 over 9. See, you could do, hey, 9 to the third power divided by 9. That's the same thing as 9 squared. But you're going to need a common denominator anyways, so might as well just leave it over 9. And then 729 minus 8 is 721. Over 9. There's the answer. Did you guys catch what the u limits would have been? If I wanted to have switched it over and found the u limits, they would have been 9 and they would have been 2, right? So you can either put the squiggles, or you could do placeholders, right? U of 2, gosh, and then u of 1, u of 1. Like you could put the squiggles or you could put the placeholders, or if you wanted to, you could have found what these u values were. You would have just taken the 2, plugged it in for x. 2 to the third power is 8, plus 1 is 9. So you could have found that that upper one was 9. And then if you take that 1, plug it in for x, you'd find that that lower one would be 2. And then if you have this, right, you could have just taken the u values and plugged it straight in. 1/3 u to the third power. If you plug in the 9, or if you plug in the 2, right, it doesn't matter. You can either do the calculations kind of at the front end to switch to the u limits and then plug the u limits in for u, which will get you straight to this step. Or if you reverse substitute, when you plug in the x limits for x, you will then have to do the calculations, which will still get you to the same point. You're going to do the same amount of work either way. It's about the same level of difficulty. So whatever you prefer, whatever makes you feel all warm and fuzzy, there you go, right? I like the squiggles. If you want to find the u values, that's fine. Everything is defined by this initial u equals equation. Okay, one more. Ooh, and this one's an indefinite. I love indefinites, right? You just put plus c, and then you wouldn't have to do all this extra arithmetic and computations. How wonderful that is for us. This one would also be a u substitution. This is the u. There's its derivative. It doesn't match perfectly, but it's going to be close enough to work. There we go, not being horizontal again. So here the u would be 2x cubed. The derivative of that should have been 6x squared. So I was supposed to have a 6. Since that 6 is missing, but it's since it's supposed to be there, but it's not. This pin's about done. It's okay. It just means a 1/6 on my original function explains why it was missing. So this is 1/6 cosine of u du. Think what would give you a positive cosine as the derivative. We're looking at the derivative, trying to work our way backwards. If the derivative is positive cosine, that means the original function must have been a positive sign. Don't forget your plus c, and then reverse substitute 1/6 sine of 2x cubed plus c. Remember, you can always check your answers for indefinite integrals by taking the derivative. If you were to take the derivative of this, it should match what you started. If you were to take the derivative of this, it should match what you started with. Can't really check that right here. You could take the derivative of this step, and it should match what we started. But once you get all the way to the numerical answer, you can't take the derivative. The derivative of the number is just going to be 0, which, no, sorry, not going to work, right? You check the calculus work. You don't check the arithmetic work. You can check this by using Math 9 if you want to, but that's the correct answer. Okay, 2 more review questions, and then we'll get to the new stuff for today. Again, if you want to just do these on your own, pause it, and then just watch it whenever you're ready. But I'm just going to go through it right now. Here we go. I'm not going to write the u sub work. The u would be 3x, so it's going to kick out a 1/3. I know the integration of a sine is going to be a negative cosine. I know the argument is going to be the same, and I know that u sub is going to kick out a 1/3. Okay, so if you can't do that, just do the u sub work. We've done questions like this in the past, so if you need to, just ask me for help. But otherwise, hopefully we can skip some of the u sub work sometimes. But there's the integration. Now I could plug it in. So I can have the negative 1/3 here. Look, I'll factor it out. So I'll have cosine of 3 times pi over 6. That's my upper evaluation minus cosine of, plug in the lower evaluation, 3 times 0. So I have the negative 1/3 kind of just out there on the front. Then I have the upper evaluation. Then I have the lower evaluation. Let's see, 3 times pi over 6. That's going to be, oh my gosh, that's going to be cosine of pi over 2 minus cosine of 0. I'm running out of room. Let me kind of jig and jag up there. So I've got the negative 1/3. Cosine of pi over 2. Pi over 2 is at the top of the unit circle. The cosine of it is 0. The cosine of 0, that's over here. The cosine of 0 is 1. So I have 0 minus 1. So all this is negative 1. The 2 negatives will cancel, giving me the answer as a positive 1/3. Okay, and then the last one, which is also going to be a u substitution question. Here I would set this piece as the u. So I'd have sine, not sine cubed. We only have one extra cosine, so just one of the sines. Sine of 5x is u. So then du should be 5 cosine 5x dx. You have the cosine piece. Very good. You have the dx piece, very good. You're missing the 5, that's okay. We can always live being off by a constant. That just means a 1/5 is going to kick out to the front. So here I would have a 1/5, squiggle to squiggle, and then u to the 3rd power du. That's what the integral translates over. I could find the squiggles if I wanted to, by just plugging in the x values, but I'm just going to do the squiggles. Okay, integrating, we would have 1/4 u to the 4th. Then I'm going to reverse substitute, so I've got 1/20, and then I'm going to have sine of 5x to the 4th power. Once I'm back to x's, then I would go back to having the x limits, 0 to pi/20, and then I would go through and I would evaluate. Here we go, we have the upper evaluation, so I've got 1/20 sine, let's see, 5 times pi/20, so it'd be 5 pi/20, that's pi/4. So sine of pi/4 to the 4th power minus 1/20 sine, 5 times 0 is 0, that's really lovely, to the 4th power. Now, here's the angle 0. We just did it. The sine of 0 is 0, right? Sine of 0 is 0. Cosine of 0 was 1. Sine of 0 is 0. So all of this is going to cancel. All of that's 0. So then we would just need this chunk. So I have 1/20. The sine of pi/4 is root 2/2. But that's the same thing as 1 over the root of 2. Right? Sine of pi/4, that's root 2/2. I'm going to use the kind of the easier version. I'm going to use 1 over the root of 2. And then minus 0, right? And then we don't really have to write that. All of this part, that's your root 2/2, or your 1 over the root of 2. And then we still need to take that, raise it to the 4th power. If you wanted to do it the longer way, like you could have, it really doesn't make that much difference. But here we go. 1 to the 4th power is 1. Root of 2 to the 4th power. Let's think about this for a second. If I had root of 2 to the 4th power, that's the same thing as 2 to the 1/2 to the 4th power. So that's the same thing as 2 squared, right? When you have a power to a power, you'd multiply 2 squared, so that's 4. So all that's 4. If you wanted to, you could just write it out, right? Like this is 2, that's 2. 2 times 2 is 4, right? It still works. Or if you wanted to, you could do the root of 2 over 2, and you could raise all of that to the 4th power, but then this would be 4 over 16, which is still going to get you the same 1/4. Oops, I'm off the screen. Right, so I used, instead of using root 2/2, I used 1 over the root of 2. Those are equivalent. They're the same thing. I just think it's easier to use this one because you have 1 to the 4th, which is easy. You have the root on the bottom, okay, which was 4. So you end up with the 1/4, which means the answer is a 1 over 80. If you wanted to use this version, root of 2 over 2 to the 4th power, right? That's your 4, 2 to the 4th power, 16. Then that would still reduce to your same 1/4. You should end up with 1 over 80, regardless of how you do it. I just think it's a little bit easier to use this one as opposed to this one. They're equivalent, so it doesn't matter which one you use. But there you have it. All right, so those 10 questions were hopefully a good little bit of review for us. Good practice. Now we're going to get to the new stuff for today, which is the second fundamental theorem of calculus. What happens if I take the derivative of an integral? Right? What happens if I do the integration and immediately after integrating I take the derivative? Well, let's think about something kind of conceptually. I do have blank space on the back. That's lovely. If I were to take x, and if I were to add 5, and then immediately after I were to subtract 5. So if I were to do one thing and then immediately undo it, like, okay, they would cancel. You end up with what you started. Or if I were to take x, if I were to multiply by 7 and then divide by 7, like they would cancel and you end up with what you started. If you do one thing and then you immediately, right after, subsequently, immediately in the next step, if you compute the inverse operation, we know in math that those two things just reverse and they undo each other, right? So if I do one thing and then I immediately do the inverse, I end up where I started. Now there's a little wrinkle for these calculus questions. We know derivatives and inverses are inverses of each other. So let's see what happens. If I integrate and then I take the derivative in, and I'm thinking that it's probably just going to cancel. But we have to watch out for a couple of wrinkles. We're going to see kind of the rule, then we'll see what happens with the 2 wrinkles, and then we'll get into these examples, and these are going to be quick. That's the last thing for today. But here we're going to actually go out and do the work to kind of show what this pattern is, what this rule is, and then when we actually do the questions at the end, you won't need to do the work. You can just get straight to the answer. All right, here we go. So we're going to do the integration part first. Once I've finished with the integration, then I'm going to take the derivative. But we're going to do the integration part first. I'm just going to leave that here. Now, if I integrate, it would be 1/3 t to the 3rd power. That's evaluated from 1 to x. Still not done, right? I have to now evaluate it. So I still am going to just copy that derivative notation. Then I'm going to plug in the 1/3, plug in the x, and then plug in the 1. So I'll have 1/3 of x cubed minus 1/3. Let's see, a 1. So that's just 1/3. So now I'm done with the integration, right? I fully integrated. I got 1/3 x cubed minus 1/3. Now what I want to do is take the derivative of all this stuff. I know the derivative of this constant, that's just going to be 0, so it goes away. Now I'm just going to do the derivative of 1/3 x cubed. That 3 would multiply to the front, and then I would get x squared. Okay, and let's do the next one. If I were to do this integration, remember I'm just going to copy the derivative for now. I'm going to do it in just a minute. But if I were to integrate cosine of t, that would be sine of t, and then evaluate it. So there's the integration. Now I need to evaluate it. So plug in x. So I'll have sine of x minus sine of pi over 6. And then let's go through and finish this. The derivative of sine would be cosine. Now, sine of pi over 6, you're thinking about your unit circle. Sine of pi over 6 is 1/2. And then the derivative of 1/2, once again, that's going to be 0. Even if this was like pi over 3, or if that was a pi over 4, it really doesn't matter, right? Since that's a constant, the derivative of that constant is going to be 0. Just like how that 1/3 went away, this sine of pi over 6 is also going to go away. And I'm going to get just the cosine as the answer. So let's go look. How does my answer compare to the thing that I started with? Right? How does my answer compare to the thing that I started with, right? We did the integration, then we took the derivative. Here I started with t squared. Then I integrated, and I ended up plugging in x, but then I took the derivative. But if I started with t squared, I ended with x squared. It's almost the same thing, but I started with t's and I end with x. Okay, let's look at the next one. Here I started with cosine of t. Then I integrated, which means at that point I took the x and I plugged it in. So I started with cosine of t and I ended with cosine of x. If I start with one thing, right, it's gonna begin with a different variable. Since the x is here, right, you're gonna eventually plug that x in and your answer is gonna end with x. That means you have to begin with something else, right? You can't have an x in the function that you're integrating and as a limit for which you're integrating. So since the x is up here, that's what we want to end with. That means this has to start with literally any other variable, right? So typically it's going to start with t's. So it starts with t, but then it ends with x. Otherwise, it's the same thing, right? T squared became x squared. Cosine t became cosine of x. If I integrate and then immediately take the derivative, if I do one thing and then subsequently follow it up by taking the inverse operation, of course, it makes sense that those two things are going to cancel. Generally, you just have to cancel and then take this x, plug it in for the variable t. Okay, that's your rule for your second fundamental theorem of calculus. If I'm taking the derivative of an integral, you will not have to do this process, right? You do not have to show the work. If you have a derivative of an integral, you're just going to take that function, which is going to start with t's, and anywhere you see a t, you're going to change it to x. And then that's it, right? Just change the variable t to x. Anywhere you see a t in that function, right? If there's multiple t's or if there's just the one, anywhere you see the variable t, you're going to change it to x. And then that's it. The derivative of an integral, they're going to cancel. You just take this x, plug it in. And this a is any constant. And let's think about the constant. Does it matter at all? This 1, let me scroll it back up. Yep, I'm still on the screen. That 1, when I plugged it in, ended up becoming a 1/3. The derivative of the 1/3 was 0. Okay, so it went away. If this was 1,000, that means that would be 1,000. that means this number would be different, right? I would have 1/3 of 1,000 cubed, right? But 1/3 of 1,000 cubed, that would just be some constant, right? That would just be some number. But then the derivative of some number would still be 0. Even if this was a -17, then this would be a -17. Then I would have 1/3 of -17 cubed, and that would still be some number. The derivative of that number is 0. This constant does not matter, right? It doesn't matter what it is. Positive, negative, big, small, it doesn't matter. Because when you take this number and you plug it in, you get a constant. And then when you take the derivative of that constant is 0, right? That a, this number, does not make any difference. This pi over 6 does not matter what it is, right? Because when you take this number and when you plug it in your evaluation step, you get a constant, a number in return. And then the derivative of that number, 1/2 root 3 over 2, root 2 over 2 root 3 over 2, it doesn't really matter what that angle was or what the sign of it was. It doesn't matter because the derivative of that number is 0, right? This a does not make any difference. When you integrate, you plug in the a, you plug in the constant, and your result is a number. And then when you take the derivative of the piece of the number, the derivative of that piece would be 0. Okay, so the a value does not matter. It's like the points on Whose Line Is It Anyways, if you've ever seen that show. The constant doesn't matter. Okay, so if I have the derivative of an integral, they're going to cancel. I'll change the t's to x's. That's the long story short. There's 2 wrinkles, right? We know life isn't always super easy. There's 2 wrinkles for this. Let's go look at them. Next example. Again, we're going to kind of do it the long way, and then really you won't ever have to do it the long way again. We're just kind of doing it the long way to try to see why these wrinkles are the way that they are. Here we go. I'm going to integrate, and then once I'm done integrating, I'll take the derivative. But I need to just carry this derivative notation first, then we'll be okay. Integrate, so it's 1/3 t cubed. Now this one's got the x on the bottom, the 4 on the top. Now I need to evaluate. Still haven't done the derivative, so that notation is just carrying. So I'm going to have 1/3 of 4 to the 3rd power. 4 to the 3rd power is 64. So I have 64 thirds minus 1/3 of x cubed. Okay, now the derivative of this piece, that's going to be 0. So I have 0 minus, right now we finished the integration. Now I'm going to take the derivative of this stuff. The derivative of the number is 0. The derivative of negative 1/3 x cubed would be negative 2x. So I have 0 minus 2x. I end up with negative 2x. So check it out. Here I started with t squared. Ooh, that's definitely wrong, right? I totally made a mistake, and I don't want to have to redo this whole video, so here I'm going to fix it. The derivative of 1/3 x cubed is not 2x. I was thinking about the x squared. I was trying to do too much in my head. Right, that's x squared. The derivative of 1/3 x cubed would be negative x squared, right? That 3 would multiply to the front, cancel the numbers. 3 minus 1 is 2. So then this answer would end up being negative x squared. I'm glad I caught it. I tried to do too many derivatives in my head, right? Don't do that. That's silly. So here I started with t squared, and I ended with negative x squared. I don't end up with the exact same thing, but I end up with the negative version of what I started with, right? I started with t squared, ended with negative x squared. The reason why that one's off by a negative is because of the order for this integration. By the way, the 4 doesn't matter. Right, that 4, when you plug it in, becomes a constant. The derivative of constant is 0, right? That 4 doesn't matter. Doesn't matter at all. But the fact that the constant was on the top and the variable was on the bottom, that order makes a difference because that variable being on the bottom means it gets plugged in second, which means that part gets subtracted, which means that whole thing is off by a negative. Okay, again, the a value doesn't matter. When I'm taking the derivative of an integral, essentially they're going to cancel. I'm going to take this function, and anywhere you see a t, you're going to change it to x, right? Anywhere you see a t in this function, you change it to x. But here, when that variable part was the lower limit for the integration, that whole thing is going to be off by a negative. Make sure, if you have multiple terms, that one's nice. It only had the one term. If you had multiple terms, like if you had a t squared plus 5t, right, you'd have to have both of those terms in parentheses, and it would all be off by the negative, right? The whole thing is off by the negative. Since it's only one term, you don't really need the brackets or the parentheses. But if you have multiple terms, that negative would distribute to everything. All right, so there's your first wrinkle. If the variable stuff that you're plugging in, if that's the lower limit for the integration, you change the t's to x's, And then you put the negative all the way out in the front. It's going to affect the whole thing. Second wrinkle, and this is the last little bit of notes today that we just practice. If I have g of x, so if I have some function, or I guess we need to do this one first. So if I have x squared and then the pi over 6 cosine, right? Let's go through and do it. We're going to do the integration first, 2 steps. Once I'm done with the integration, then I'll take the derivative of it. The integration of cosine is sine of t. And then here we go. That would be, still haven't done the integration completely yet, so that derivative is just waiting its turn patiently. Sine of x squared minus sine of pi over 6. Again, now we're going to take the derivative of it. That piece doesn't matter because the derivative of that constant is going to be 0. That pi over 6 still doesn't matter. The only thing that matters is the variable part. Now here, let's take the derivative of sine of x squared. The derivative of sine of x squared is going to be cosine of x squared, but then you would need to do chain rule times the derivative of that inside piece. So I started with cosine t, and I ended with cosine of stuff. I ended with cosine of x squared, but then I needed to do chain rule, right? So what happened was this x squared, that variable part, plugged in for the variable t, right? Instead of cosine t, have cosine of stuff, whatever that stuff was, you plug it in for the variable t, but then you needed to do chain rule. You needed to account for the derivative of that inside piece. You needed to account for the stuff that you plugged in. Okay, so here we go. This last rule, whenever I have g of x, some other function, right? Again, the a doesn't matter. This constant doesn't matter. And when I take the derivative of an integral, they're going to cancel. But what I'm going to do is I'm going to take this stuff, whatever it is, I'm going to take this stuff and plug it in for the variable t. So I'll have f of g of x. Whatever this whole thing is, you're going to plug it in for the variable t, but you need to do chain rule times, and that whole thing would be times the derivative of that inside piece. Now, what this piece becomes, like notice, I took this x squared and I plugged it in. That became sine of x squared. And then when I needed to do chain rule, it was just 2x. I didn't have to do chain rule for cosine of x squared, right? Once I take this thing and I plug it in, it doesn't matter what this piece becomes once you plug that stuff in. Chain rule comes from the piece that you're plugging in. Once you take this thing and you plug it in for t's, you do not do chain rule of this whole thing. The only thing you do the chain rule for is the piece that you plug in for t. It's the variable part of that integration, right? So this is a really easy rule. This fundamental theorem, second fundamental theorem of calculus. If I take the derivative of an integral, some stuff's going to cancel. You just have to watch out for when you need a negative. That happens when the variable or the variable chunk is the lower limit of the integral. And you also watch out for when I need to do chain rule. And that happens whenever your variable piece has a derivative other than 1. Okay, so let us practice. These second FTC questions are really quick, really easy. They're literally about 5 seconds each, maybe 10 seconds if your pencil or your pen breaks halfway through, but they're really easy. If I take the derivative of an integral, they're going to cancel. And then I just change the t's to x's. So here's the function that I have. I'm going to take this t, or I'm going to take this x and then plug it in. So the function was square root of 1 plus x squared. That means my answer is going to be the square root of 1 plus, but instead of 1 plus t squared, I'm going to change the t's to x's. So I have the square root of 1 plus x squared. Do I need a negative? No, because the x was on the top. If this order would have been switched, then I would have just put the negative out in front, but I don't need it. Do I need chain rule? No, because the piece that you plugged in was x, and then the derivative of x is 1. So that's it. You just change the t's to x. That's it. That's all you have to do. Okay, example B. Let me keep that on the screen for you. Here we go. I've got the derivative of the integral of tangent of t cubed. So I start off with tangent of t cubed. What I'm going to do is take this x, plug it in for the variable t. Not that t, right? That's not a variable t. That's just part of the tangent. I'm going to plug that in for the variable t. So I started with tangent of t cubed. I'm going to end up with tangent of x cubed. Remember, you're going to end with x's. That means this has to be something besides x. It could be t's most of the time, or if this was a p and that was a p, that would be fine. You would just change the p's to x's. It doesn't really matter what this variable is. The one up here is what you're going to end up with. Okay, but since this is an x, these cannot be x. It has to be anything else. Most of the time it'll be t's, but it doesn't have to be. But if x's is here, this has to be something else. Okay, so there we go, right? Just change the t's, the variable t's, to x. Do I need a negative? No. If these orders would have been switched, if it would have been x to 2, then I would have needed the negative out in the front. But since the x was not on the bottom, I don't need the negative. Do I need to do chain rule? No. Okay, if this would have been, let's say, how about 2 to, how about 5x plus 1? Then I would have done is I would have taken this, plugged it in for t, so I would have had tangent of, then I would have had, instead of t cubed, I would have had 5x plus 1 cubed, right? Whatever this part is, I would plug it in for the variable t, but then I would need to do chain rule. The derivative of this piece would be 5, so then I would just write times 5. Okay, so if you have to do chain rule, that's fine. You just whatever you have to do, plug it in for the variable t, and then if you plug that thing in and you're like, hey, Mr. Bell, the derivative of that thing that I'm plugging in, that's not 1, then you just do chain rule. Okay, but it wasn't like that. You didn't have to worry about the negative because the x was on the top, and you didn't have to worry about the chain rule because it was just a regular x. So here we go. Tangent of x cubed, that's it. That's all the answer is. Example C. Here I've got 1 over 1 plus t. I'm going to take the derivative of this integral. I know those are going to cancel, right? The 3 didn't matter. This 2 didn't matter. This negative 1 doesn't matter. What I'm going to do is take this stuff and plug it in for the variable t. So I'm going to have 1 over 1 plus, instead of t, plug it in. But now I'm going to need to do chain rule. So you can either put this in parentheses and then have your 3x squared over on the right, or if you want, you could put the 3x squared on the top, and you could write the answer like this. Both of those are equivalent. I don't really care which one you do, but you're going to take this function, which starts off with t's, change the t's to whatever this stuff was. And since the derivative of this piece is not 1, you need to make sure you do chain rule, right, which is this piece right here. Again, if the order would have been flipped, if the x cubed was on the bottom, and then the number was on the top, the only thing extra you would have needed, right, would have been the negative. If this happened, all you would have needed was the negative. Since the x was on the top, you don't need the negative. Okay, last one, and then we'll be done. The derivative of the integral of this stuff. I've got the cube root of 1 plus t squared. So here we go. I've got the cube root of 1 plus stuff squared, right? That's what my function was. Cube root of 1 plus something squared. I'm going to take this sine of x and plug it in for t. And then I think to myself, is the derivative of sine 1? No, it's not. The derivative of sine is cosine. So I'm just going to put that chain rule. You can either put it on the right or out in the front. It doesn't really matter. But I'm just going to change my variable t to whatever this stuff is. Just watch out for the negatives, which I didn't need on any of these examples. And then you watch out for the chain rule, which I did for the last two. Right? So the second FTC, change the t's to whatever that variable chunk, right, in your integration. Whatever that variable chunk is, you plug that in for t. You just watch out for needing a negative, if that's going to happen, if your variable chunk is on the bottom, or you watch out for needing chain rule. Change the t's to whatever, watch out for the negative if you need it, watch out for the chain rule if you need it. That's it. Your second FTC homework, most of it is going to be kind of just a review, right? Just some practice with derivative questions, some practice with some integral questions. The new stuff, the second FTC questions, those should be really fast and really easy. Change the t's to whatever that stuff is, watch out for the negative, watch out for chain rule. And remember, your chain rule, it doesn't come from this stuff, right? Once you take that thing and you plug it in, what it becomes afterwards doesn't matter. Chain rule comes from the thing that you plug in, not what it becomes after you plug it in. It comes from the thing that is your limit on your integral.